Thanks, guys. It's nice to meet you all. My name's Angus. I'm a core contributor working on analytics for Tesseract and YieldJack, and I'm here today to talk about how Tesseract helps solve interoperability on Avalanche. The first thing I want to say is that building Tesseract was very much a team effort, and the plan is to talk a little bit about the Tesseract smart contracts, which we've called cells, and how those work, as well as our front end and routing. I'll do my best to answer any questions if we have time at the end, but fortunately we do also have pretty much the full team here, so there's room for detailed discussions afterwards in case we run out of time. So for those who've been here for previous talks, this might be slightly repetitive, but I'll briefly touch on how ICM contracts, and ICTT, which are built by Avalabs, work as Tesseract builds on top of these. So first of all, ICM, interchain messaging, is a cross-chain communication protocol that lets messages be sent between Avalanche LV1s. For the EVM, this makes use of the warp precompile, which is a special kind of contract that's implemented directly in the node software, unlike most smart contracts which are written in Solidity and then deployed as bytecode. You can think of it as kind of built-in functionality for Avalanche L1 EVMs. Unsigned messages are sent to the precompile, and an off-chain relayer listens for new messages, aggregates signatures, and then passes on these messages as part of a transaction to the destination chain. How it works is quite complex, with using things like BLS signature aggregation that Michael and others spoke about earlier, and some other details that are quite conceptually difficult. But fortunately, Avalabs built ICM contracts, also known as teleporter messenger, to abstract a lot of that away, so that smart contracts built on top can just call functions like send cross-chain message to send messages, and can receive messages by having the required interface, the required receiver interface implemented. So they don't have to worry about signature aggregation and similar types of things. You also get some additional properties like protection against multiple delivery, relayer incentives, and message execution, which is the key extra thing that helps Tesseract. It's deployed at the same address on all chains, so it makes it easier for relayers. Then on top of that, you've got ICTT, which is interchain tokens transfer, and is a set of smart contracts also built by Avalabs, which make use of ICM contracts in order to specifically transfer tokens between L1s. You've got home contracts, which sit on the home chain of the token we wish to transfer, and there's also remote contracts, which sit on the many or various L1s to which we want to send the token in question. There's a one-to-many relationship between homes and remotes, and there are corresponding contracts for native and ERC20 tokens, as Chris mentioned. The main functions in these contracts in which we're interested for compatibility with Tesseract are send and call. The calling of each of which then calls send cross-chain message on the teleporter messenger contract, encoding various attributes within the message, and in the case of send and call, also a payload, which is going to be important. Then teleporter messenger makes a call to the warp precompile, which causes the warp precompile to emit an event. A relayer listens out for these events, aggregates the signatures, and then calls receive cross-chain message on the destination chain's teleporter messenger contract. It's first verified by the warp precompile, and then the teleporter contract further calls receive teleporter message on the recipient contract, which will be the home or remote ICTT contract, depending on the direction of the sending. And then the included message is decoded, and standardized fields like the message type can be passed, for example, in order to determine whether it's a send or a send and call from the origin ICTT contract. If it's just a send, then it will just mint new tokens if it's a remote contract, or release collateral if it's the home contract. But if it's a send and call, then the contract handles this by passing arguments, including the previously discussed payload, to another contract, which must implement a send and call receiver interface, which basically means these contracts have a receive token function that takes the expected arguments and can then do something further with the payload. So this allows for pretty unlimited and arbitrary levels of functionality between L1s by making use of ICM and ICTT, and is where we start in the explanation of the Tesseract contracts. So we know that contracts which implement the send and call receiver interface can receive instructions from a message passed between L1s using ICM and ICTT, and can then act on it or do something. If these instructions contain information about how to execute a trade, and we've also received some amount of the relevant token to actually carry out that trade, then we're pretty much there conceptually, and this is pretty much what happens in Tesseract cell contracts. The set of instructions for carrying out a cross L1 swap or transfer across arbitrarily many chains are structured in an array of hops. So each hop can be thought of as an individual instruction for what a sequence of cell contracts needs to do. It could be as simple like send tokens to this other chain, or send tokens to another chain and then do something else, or make a swap on this chain first using this trade data, and then send the output tokens to another chain, or possibly just deliver the output tokens to an address on the current chain. The big struct of instructions that's passed to the cell is passed to the cell contract as an argument to the initiate function. There's some checks and basic initial actions that happen here, such as the creation of a unique Tesseract ID, which is useful from my perspective for analytics, before the full payload is then passed to the root function. This is where the bulk of the action happens. If there's a swap to be carried out, then exactly what is done will depend on the type of cell being called. And which type of cell is being called depends on the instructions. Now, what do I mean by type of cell? It's worth saying at this point that we have multiple implementations of the cell contract, which all inherit from a common base cell contract. So at the moment, there's a yak swap cell, which makes use of the yak router, basically using yak swap behind the scenes, which I'm sure many are familiar with. We also have a univ2 cell for the scenario that an L1 just has a basic univ2 fork deployed on their chain. And we also have a hop-only cell for the scenario that there's no DEX on the chain, so no swaps being carried out there, and it just allows for hops on and off, or transfers on and off. And finally, we also have a DEX-lot cell, which is a pretty niche implementation that our smart contract dev, Simon, and front-end whiz, Harry, who are both here today, have made work in order to have DEX-lot integrated with Tesseract from day one. So back to the routing, after any swaps have been carried out, we then finally either just send the tokens to the recipient if it's a same chain swap, or if we're going cross-chain, then the cell will now either call send or send and call that were discussed earlier as part of the ICTT contract overview. And at this point, it's probably very helpful to combine the new information about cell contracts with the diagram previously. So here we see the steps for an ICTT transfer between L1s, as described earlier. When we add the functionality brought by Tesseract, it looks like this. So we start by calling initiate on the cell contract, which then routes, maybe via yak swap, before then proceeding as before with the rest of the ICTT flow. Currently, it shows what happens in the case of a pretty simple interaction with Tesseract, as we're only doing a single cross L1 transfer. In this case, the function used on the ICTT contract would have just been send. You may remember I mentioned the send and call receiver interfaces. These mean that on the destination chain, the relayer calls receive cross-chain message on teleporter messenger, which then calls receive teleporter message on the ICTT contract. And if it's come from a send and call, which is figured out in the message type, then it's directed towards the relevant cell contract on this destination chain and calls receive tokens, which then allows the payload to be executed. So when receive tokens is called, the cell payload is decoded and the root function is invoked, which then potentially results in another swap. So at this point, we might be finished, and the output tokens from the swap might just be sent to the user. But if there's more cross-chain transfers left to do, then the cell will be using send or send and call again, and sending the tokens and possibly payload to another L1. On this L1, you have the same actions as before, with the relayer listening out for events. And if a final additional swap is needed, then it will call receive tokens again on the cell contract, and then route and maybe swap. But otherwise, it will skip this step and just go straight to the user. So hopefully with that, you can kind of see a bit of an overview of the full sequence of contract interactions, which can and should carry on until all of the arbitrarily many hops in the array that's part of the instruction struct have been completed. The natural next step after seeing this, in my mind, is the natural next question, is, okay, cool, but how do I build up this instruction struct? The short answer for most users is that if you're using our front end, another shout out to Harry, then you don't need to worry about these things because it's already done for you. For those who want to know a bit more about how exactly it does this, I'll give a bit of an explanation. So ultimately, the problem we're trying to solve is efficiently finding possible paths and then querying these paths to find the one with the highest quantity of the output token on the destination chain for the user. At the moment, we take a pretty exhaustive approach to this for pathfinding. Starting with the origin chain, we check all ICTT contracts that allow transfers to other L1s, like any other L1s, having a swap from the origin token to the ICTT transferable token first if needed, and then from each of those destination L1s, we're checking for more possible ICTT tokens that allow further transfers to other L1s. This could even be back to the same one, as you can see in the example here. And then it keeps going and repeating this until we reach our predetermined maximum number of hops, at which time we exclude any routes that don't end up with us on the desired destination chain, and we might have one final swap on that destination chain in order to get to the correct output token. So the number of possible paths is proportional to the product of the number of L1s and the number of ICTT links between those L1s, all raised to the power of the maximum allowed number of cross-L1 hops. So in searching for possible paths, increasing the number of cross-L1 hops that are allowed means an exponential increase in the number of possible paths. Then all of these paths need to be queried, and in some cases where we have multiple swapping cells deployed on a chain, so on C-chain, for instance, we have a yak swap cell and a deck slot cell because tokens can be swapped via either, then it's another kind of duplication of possible paths. Optimizing all of this is a key area of focus for Tesseract going forwards, and I mean, even since I made this presentation, there have been some improvements. Again, shout to Harry. And saying all of that is without even mentioning the existing optimization that happens as part of the yak swap cell, which uses the yak router contract, and it is already finding same chain optimized paths for swapping between two tokens. So now I've spoken about the smart contracts and routing, I think it's time to talk about how to use it, which, thanks to the slick UI, is relatively straightforward. Our website is at tesseract.finance, and upon visiting this URL, users should be greeted with a pretty familiar-looking interface that should be intuitive to use. There are drop-downs to select the input and output tokens and chains, and once you've done that, you can then review the proposed path, which allows you to see slightly more detail on what's happening in each step, as you see there. And then once you click swap, and there's a signature going on over here that you can't see, but then it will initiate the first transaction. And as sequential transactions are executed by relays on other chains along the way, it will update the progress until eventually the whole thing is completed, which shouldn't take long there. So that's an example of a swap from AVAX to COC on COCNet. Now, it hopefully looks pretty simple, but behind the scenes, there's quite a lot going on here to track everything. You've got multiple transactions being executed across multiple chains, and in order to be able to say these are linked, there are a lot of checks for certain events being omitted. One addition we made to help with this and to help with analytics was the creation of a Tesseract ID, which is made during the initiate call and then passed as part of the encoded messages, and then also emitted as part of each cell-rooted event. This makes it slightly easier to piece together transactions on disparate chains, primarily relying on only our own events, although there are some small cases where we also have to check for other contract events, but not too much. The next and perhaps most important thing I want to talk about is the process to get a new L1 integrated with Tesseract. The first requirement is that you're using ICTT or plan to use ICTT for transferring your token or tokens across Avalanche L1s. The official Avalanche docs for setting up these contracts are very thorough, but we'd also be able to help with this if needed. Depending on your setup, you might need to deploy a token home contract on your own chain and token remotes on other chains, or you could potentially use an existing token home on the C chain and make a new remote on your own L1, if, for example, you wanted to be able to transfer AVAX to your L1, And these kinds of decisions and thought processes are definitely things we can help with, so I'd recommend reaching out to the team as quickly as possible. Excuse me. Then once you've got your ICTT contracts deployed, all you need for Tesseract to work is for us to deploy one of our cell contracts on the L1, or you can deploy it yourself and make us the owner. Either way is fine. And which contract you should deploy depends on whether you've got no DEXs on your L1, in which case it's just hop only. If you have a very basic DEX, like a UniV2 fork, then we can use our UniV2 cell. If you have a different type of DEX, we can make a cell for that as well. And if you have multiple DEXs, then we'd maybe use a YAK swap cell and a YAK router contract. In reality, we expect most would only need either the hop-only cell or maybe the UniV2 cell or similar. That's because we expect most of the liquidity to be on the C chain. Once that's done, it's just a case of us adding in the relevant info to a config file on our front end, and then we're all good to go. So I think an important point to raise here, now we've kind of gone over how it all works, is why you should use Tesseract as a prospective L1. The primary benefit is that your users can access C-chain liquidity without having to leave your L1. This means you don't have to worry about deploying and maintaining DEXs yourself, nor do you have to worry about transferring enough liquidity of, say, AVAX from C-chain to your own L1 and like managing that. Instead, your users can trade via C-chain liquidity, all accessed from your own L1. So for example, if a user on the player L1 network has like some native player tokens, but wants or needs some AVAX on that chain in order to purchase some gaming-related NFT on some game that uses the network and only accepts AVAX as payment, then they could use Tesseract to transfer the player token to C-chain, make a swap in the Pharaoh AVAX player pool, and then bridge back the AVAX to the L1 network all in a single click without even feeling like you've left the network. So that means no worrying about executing multiple transactions or managing gas tokens and RPCs for other chains. Another advantage of integrating, is that you get exposure to potential new users. So with Tesseract as a core tool for interacting with the overall Avalanche ecosystem, which we hope it will become, by having your tokens and L1s integrated and appearing in the drop-down menu, then more people know it exists and you hopefully will attract more users. As we improve the pathfinding and the range of options available, Tesseract should become the best and easiest way to get the best price for what could otherwise be a very complex and time-consuming series of transactions. For future steps, there's a few things we're working on. First, we want more L1s to make use of the Avalabs-built ICT technology so we can integrate them into Tesseract. The benefits become more apparent as more and more L1s are integrated. In parallel to that, improvements to the algorithm for pathfinding and getting quotes are always being worked on, as well as general UI UX improvements. For me personally, I want our analytics to be in a better place with some nice dashboards on Dune or other places, and that's pretty much it. So thanks for listening, and if there's some time, which I don't think there is, we can take some questions.
I do believe we have 2 minutes for questions, so if you have one, please raise your hand.
Cool.
All right.
I really like the presentation, but I just had one question about the path. How do you find the routes? How do you know when to swap on which chain if there are multiple hops? Like you have to go from one chain to another. How do you know on which chain to do the swap if needed?
You basically trial it with multiple options. So if there were like DEXs on one L1 and another, there will be possibly, I mean, we get quotes for all of it. Up ahead is the short answer, and then you pick the one with the shortest amount, with the highest amount. But if there's like multiple L1s that you could go through, we just try them all pretty much. It's quite an exhaustive approach at the moment. Does that make sense?
Yeah.
Is this calculation frozen, or do you have
It's not frozen. So some of the optimization that's gone on recently is kind of, one thing is to reduce the possible intermediate tokens so that you reduce the number of possible paths. But you can ask Harry for more details afterwards, but the way I understand it works is that we kind of preload all of the possible paths ahead of time and then fetch the quotes live. And then you basically pick the path with the quote with the highest number of output tokens for the user.
Perfect. Very cool.
Awesome. Any other questions? I have one question. So I remember you mentioned something like if you want to use it, you deploy it yourself, and then you make it. You make the Tesseract team, I think, the owner of the contract.
Yes.
So we'd love to learn like a little bit what the vision there is. Do you see eventually coming like a permissionless deployment, the permissionless joining that ecosystem, or is like what's the plan going?
I think we're pretty flexible on that, really. Like the idea of being owner is that for the more complex transactions, we're going to be taking a fee, a small fee. For simple bridging, there'll be no fee; it should be free. But for things where we are genuinely adding value to the user, there'll be a small fee, which is why we need it. Are one of an EOA or address controlled by us as the owner. But yeah, I mean, the other thing as well, we do need to slightly control which L1s we work with, because we need to trust them to an extent, because otherwise there can be all kinds of potential attacks. So if they're listed on Tesseract, it's some statement of trust and validity. So I don't think it can probably be completely permissionless, but yeah, we'll see.
Awesome. All right. Any other final question? No. All right. Thank you very much, Angus, for the presentation and the whole Tesseract team.